All right, good morning. Today we'll be talking about chemical bonding. The first type of bond we're going to look at is ionic. We have two types of chemical bonds, ionic and covalent. We're going to be looking at ionic today. All right, so for chemical bonding is pretty awesome because this is where we're able to start a lot of our new chemistry, and this is where chemistry comes to life for me. So for chemical bonding, there's only going to be two reasons why a chemical wants to bond. For one, he wants to satisfy the octet rule. That means he wants to have a full outer shell. So with his valence electrons, he want to maximize those. And it also increases his stability. So the octet rule means you have a full outer shell like the noble gases. So if we look here, these ones all have full outer shells. Helium, neon, argon, all of these are full outer shell. Those are really, really, really stable, high stability. So as we satisfy the octet rule, we also increase stability as well. So the octet rule just means I have a full outer shell. So let's look at a couple elements. So here we have lithium. Lithium has 3 protons. He also has 3 electrons. 2 in this first shell. This second shell can hold 8, but it only has 1. So he would need 7 more electrons to fill it up and become like neon, the noble gas in the row. All of these are row 2 elements or period 2. And so they all have 2 energy levels. These ones are getting smaller because they have more protons. This one is the smallest because he has the most protons. He has a full outer shell. He satisfies the octet rule. He has 8 electrons. Or lithium can lose 1 electron and become like helium. This is the first noble gas. So I'm looking at periodic table, so we have neon, helium, fluorine. So these are my noble gases, and then here, this is lithium. Lithium is going to try and become like helium or neon. So then I want to decide, is it going to be easier for him to gain 7 electrons and become like neon, or is it easier just to lose 1 electron and become like helium? Well, it's going to be easier to lose 1 than it is to gain 7. So this one wants to lose 1 electron, so he's going to get rid of this electron. So he's kicking it out. And then now we'll see lithium still has 3 protons. And then it's going to be a little bit smaller now because he lost that energy level. So now I have 2 electrons. Now I'm just like helium. So I have a full outer shell. I've satisfied the octet rule. Helium is special because he's not able to put 8 in there, but he has a full outer shell satisfying the octet rule. And then everything else wants to have 8 in their outer shell satisfying the octet rule. So lithium lost 1. Now he's like helium. Now he's stable. But electrically, he's not neutral anymore. So now if I look at that, this one has 3 protons, so we have proton, proton, proton. Only 2 electrons, electron, electron, so we cancel, cancel. And we have a 1 proton charge. So that tells me that the charge on this one is going to be 1 plus. So he's an ion now. So this is a cation. That's an ion with a positive charge. All right. So now this one is ionized here. Yeah, this one is ionized. All right, then the next one we're going to look at is fluorine. So fluorine is sitting here, and he can do the same thing. I can either gain 1 electron and become like neon, or I can lose 7 electrons and become like helium. The elements are going to try and become like the closest noble gas. The closest noble gas is going to be neon. It's easier to gain 1 electron than it is to try and get rid of 7. So look here. Oh, lithium just happened to kick 1 out. So let's take that electron that's floating around in the universe. Could have been any electron. And we'll give that to fluorine. So now, fluorine, we're still going to have 9 protons. This first shell still has 2 electrons. And And now the second shell has gained an electron, so he's going to gain some size too. So as I gain this electron, I did get a little bit bigger because now I have more stuff we need to spread out. Give me some room. I'm a big fella now. But I noticed that we have an imbalance of protons and electrons. So now we have 9 protons, 10 electrons. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we get cancel, 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 cancel. And then we're left with 1 electron, so this is a 1 minus charge. So now this has 10 electrons. He's stable because he has a full outer shell like neon. So now we have 2 electrically charged elements that are stable. So they're not neutral, but they are stable. So we have lithium. This has a 1 plus charge. Fluorine, this has a 1 minus charge. So these charges now, they're electrically attracted to each other. They're ions. And then we form a bond based on our electrical charges, the opposite of charges. And we'll have lithium, fluorine. And then this would be, first name stays the same. Second name gets IEE. All right, so let's look at something like oxygen. So if we have oxygen, he likes to gain a 2 minus charge. And let's compare with something like potassium. Potassium has a 1 plus charge. So when they bond, they do need to be electrically neutral. They're trying to balance out the charges. So here we have K with a 1 plus, oxygen with a 2 minus. So we're going to need 2 Ks to balance that out. So now we have a net charge of 2 plus. Over here we have a net charge of 2 minus. So this would be K2O. And then another way I can do that is if I just look at the charges, if they're different, I just do a cross and drop, and we can get the chemical formula like that, K2O. So that's a little bit about chemical bonding, satisfying the octet rule, increased stability, and also when I look here, increasing stability. So everything in the universe wants to increase stability. We'll also see a term called entropy. All right, so entropy wants to maximize randomness or increase stability. And when we look at the universe, the only thing that's pretty uniform about the universe is that everything is different. So that's the theme that we can see. Everything is not the same. Entropy wants to maximize that because it's the most stable form. So if you look at something like the human body is highly unstable. Our human body is unstable because it's highly organized. Our human body is not random. So we have lungs in a specific place. We have our stomach in a specific place. Blood is in a specific place. Brain, eyes go here. Nose is on the front. Mouth is under the nose. So it's highly organized. But to be organized, it requires a lot of energy. So if we increase stability, that'll be a low energy state. That's something that can be maintained without pumping energy into it. So, when you go home tonight, you grab a slice of pizza. That helps your lungs stay here, your feet stay down there, your eyes stay here, your ears stay on the side. Because we're pumping energy into the system, and then your system can help organize that. If we were to stop pumping energy into this system, the universe would want to increase the stability of this, and that would be maximum randomness. So if you were to just lay down outside on the grass and not eat anything over a period of about 3 or 4 months, eventually you'd be very stable. We wouldn't have to worry about you moving much at all. And then it would maximize the randomness. So right now, like your stomach, the gastric juices, they're very acidic. So if you were to leak into your body, that would cause a problem. Oxygen has to be dissolved in the blood. If we took the form of oxygen that wasn't dissolved in the blood, like an air bubble in the needle, and pump it in, and it's not dissolved, then that would cause big problems. Your liver bile, it stays here in the back by your liver. If it comes out, it creates a big problem. Urine, feces, all those stuff have to be organized in special places within the body. And if urine and feces go into your bloodstream, you could potentially die. So this is highly organized, but if you just go out there and lay down and don't pump any energy into the system, you'll be maximally randomized. So all this will just turn to dust, and you'll have the lungs mixed with the skin, mixed with the bone, mixed with the cartilage, mixed with the ligaments, mixed with the stomach. All of this will just go back to a dust or maximum random. It'll be uniform throughout, just a big pile of dust. And eventually that's where we all go. All right, and then the two types of bondings that we'll be looking at is ionic. We'll also be looking at covalent. So if I want to know if a compound is an ionic bond, I look for a metal. So over here, metals are typically going to be on the left side. So I look, copper is a metal that's in our electrical stuff. Silver, I can wear that on my necklace. I can have a gold necklace or a gold tooth. Aluminum is on top of the refrigerator. We wrap the chicken in there. And then carbon is kind of like a piece of charcoal. Or I can go to the jewelry store and see carbon. It looks like glass. It's a diamond. So all of these are nonmetals. So this is where I start nonmetals. I can breathe in oxygen. Sulfur is a yellow powder. Chlorine is in the pool. None of these are metals. And then when I come on this side, boron, aluminum. Aluminum is on top of the refrigerator. That's foil, or we can have tin foil. So these are all metals to this side. Nickels are in my pocket. Iron is a rusty nail. Titanium is a very, very hard metal. Sometimes bicycles are made out of it. And then these are earth metals. Calcium, magnesium, sodium. All of these are earth metals. So I start my metals from boron, aluminum to the left. Non-metals are going to be carbon to the right. Typically, our semi-metals and our metalloids are more non-metal than metal. But something like silicon is used in computers. It has properties of both metals and non-metals. All right, so I'm looking to see if a metal is present, it's ionic. If no metal is present, then it must be covalent. So when I look at these ones, sodium oxide, so I'm looking for a left side element. So I look at this first one. If it's a left side element, left of carbon, so I'm looking to see is sodium to the left of carbon? Sodium is here. Okay, that's an alkali metal. So this has to be an ionic compound. We'll never see metal and metal bonding together, so we don't have to worry about that. We can mix metal and metal. That's called an alloy. So we have metal, non-metal. So we call this one ionic. So now we have, oh, this looks real similar. This is an N and an O. The only difference is an A. This must be covalent too, but let's check and see. I mean, ionic also. So here's Na. So now we need N. Wait. Nitrogen is over here. He's to the right of carbon. So carbon to the right, all of these are nonmetals. So this is a nonmetal. Oxygen is a nonmetal. If I don't see any metal present, nonmetal has to be covalent. So I'm going to label this one as a covalent bond. Calcium and oxygen. Okay. Calcium is in my bones. You saying I have metal bones? Yep. Sure am. It's not vibranium like Wolverine, but we do have metal inside of our bones, just like Wolverine, but we have calcium instead of vibranium. Maybe it wasn't vibranium. That might have been Captain America. So we have metal inside of our bones, calcium and oxygen. So that's going to be an ionic bond because I have metal present. This looks pretty similar. It has a C and an O. This must be ionic also. But let me check and see. All right, so calcium is over here. And, carbon is here. So he's to the right of aluminum. So this is a nonmetal. Oxygen is a non-metal. Okay. And when I'm breathing, I can breathe out carbon and oxygen. Carbon dioxide is something I exhale. So this is going to be a covalent bond. All right. And then as we get into nomenclature, nomenclature means naming system. So this is our naming system. We'll start with ionic bonds. So it's just like when we get married. First name stays the same, last name gets an IDE, and we'll talk about that briefly in the next video.